Today we're doing some more Calculus 2 practice problems focusing on area in polar coordinates. So, prerequisite knowledge. For a sector, the area of the sector is 1/2 the radius of the sector squared times theta, the central angle formed by the sector, right? We need to know this because if we're looking at some polar region, what we can do is make one very, very thin slice. Now we're back to slices, and that slice just has a delta theta, right? A very small theta, but it still has an r, and that r is a function of theta, right? Because this r right here is different than this r. There has to be some function of theta. For example, this would be a function of theta. R equals 5 cosine 5 theta, right? If that function represented this curve, how could you find the area between these two angles? Alpha is, if you want to just find this region, alpha is swung up from the x-axis and beta is on the other side of the region. So alpha is on one side of the region, beta is on the other side. What we can do is find the delta area, meaning the area of just this one very thin slice, just this sector. It's going to be 1/2 r is now a function of theta, and theta is instead a very small theta, delta theta, right? We can take the limit as n approaches infinity, summing up all of those delta areas, all of those little slices between alpha and beta, right? We just want all of the slices in between alpha and beta. So we can integrate between alpha and beta of that delta area, which turns to a d area in the integral. So remember, d area is just 1/2 that function of theta squared, d theta. The only tricky part in this whole process will be finding beta and alpha, because they will always give you this function of theta. So let's look at an example. Prove the area of a circle is pi r squared using polar. So this is the equation of a circle, x squared plus y squared equals r squared. We can find the area of the circle, and we can do this one of two ways. This is one way, where we just look at a quarter of the circle, or an eighth of a circle, a 16th of the circle. I'm just choosing a quarter because it'll be easy. Let's find the area of this region. Would you agree that the area of the whole circle will just be 4 times whatever this region is? Well, in polar, we're going from alpha, where alpha is the right side of the region. In this case, just 0 degrees, right? And we're swinging up all the way to pi over 2. So on top of the integral, we're going to have a pi over 2 of that 1/2. What is r? Well, for a circle, it's a constant r, right? The r is r, and then we have a d theta. So this area, the entire circle, will be represented as 4 times 1/2 times r squared. Integrate r squared with respect to theta, you get r squared theta. We're going to evaluate that at pi over 2 and 0. So the area is 2 r squared pi over 2 minus 0, because r squared is a constant. And finally we have area equals, let's see, this 2 will cancel this 1/2, and we're left with just pi r squared, right? So that we have proven that the area of a circle is pi r squared using polar. Now I said this was one of two ways. The other way is we could have just done it from here, right? Area is just the integral from 0 to 2 pi. Can't we just start at 0? So alpha is 0, right? And beta, we're going to swing all the way around to here. Beta is 2 pi. We end up in the same spot. 0 to 2 pi of 1/2 r squared d theta. We're going to get 1/2 r squared times 2 pi, and the 2's cancel. But the reason why I wanted to show it this other way is because we're going to be using symmetry. Like we could have used the symmetry of the circle to solve it. Maybe it wasn't easier in this case, but in other cases it will definitely be easier. So let's look at finding the area of this shaded region. See, they gave you R, and you can put your calculator in polar mode and graph it. But since they give you the picture in this case, let's see, area. What's in the integral is the easy part because they give you R, 3 minus 2 sine theta squared d theta. Where are we going from in 2? Well, it looks like alpha is starting here, right? This would be the rightmost. We want to encapsulate all of this, which is pinched between, it looks like, pi over 2 and down here at 3 pi over 2. So by having those bounds, we're just concerned about what's ever to the left of those, which is the region that we are worried about, right? So now let's look at solving the integral. Well, we can pull the 1/2 out, and then let's FOIL it out. We have a 9 minus, we're going to have, looks like 12 sine theta, because we have 2 negative 6's, and we have a plus 4 sine squared theta d theta. So now this will be a review back to one of my beginning videos of trigonometric integrals. But this is doable. Let's integrate 9 with respect to theta. We're going to get 9 theta. Don't forget the bounds. And let's integrate negative 12 sine theta to get positive 12 cosine theta, right? Because the derivative of 12 cosine theta is negative 12 sine theta. How about 4 sine squared theta? Well, we know that sine squared theta is 1/2 minus 1/2 cosine of 2 theta, right? So we cannot integrate this, but we can integrate this. So let's see what we get. We have a 4 in front of all of that. 1/2 minus 1/2 cosine 2 theta, but we're still integrating that. So let me pull that off to the side. We're still integrating this. So now we're integrating 2 minus 2 cosine 2 theta with respect to theta, and we're going to get a 2 theta. Let's see, when you integrate negative cosine theta, you're going to get negative sine 2 theta. And if we did a u substitution, we would end up with a 1/2 out front. So this 2 is canceled by a 1/2. And let's just check our work though. What is the derivative of negative sine 2 theta? Well, it's negative cosine 2 theta times 2. So as you can see, we did the integral correctly. So that's what's going to go here. We have a 2 theta and a negative sine 2 theta. We're evaluating that at 3 pi over 2, pi over 2. So we would like to see the cosines, because cosines of pi over 2 and 3 pi over 2 is just 0. Right, let's see. We have a 1/2, a 9 theta and a 2 theta make an 11 theta. So we have 11 times 3 pi over 2. And then we have a 12 cosine of 3 pi over 2. But like I said, that is just 0. And then we have negative sine of 2 times 3 pi over 2. So the 2 and the 1/2 cancel. What is sine of 3 pi? Sine of 3 pi is, let's see, 0, or just 0, right? Sine of 3 pi is 0. So that is f of b. Now let's do subtract f of a. We still have that 11. Now we're evaluating it at pi over 2. And at this point, you could have plugged this into your calculator. From this point right here, you could have plugged this into your integral capable calculator. And that is really all your professors can care about is the bounds. This is the main issue of this section. But let's see. Plus 12 cosine of pi over 2, which like we said was just 0. And then we have minus sine of 2 times pi over 2. So the 2 and 1/2 cancel. We're left with sine of pi, which again is 0. Okay, so let's try and do some simplification. We have 1/2. We have a 33 pi over 2 from this. And we are subtracting 11 pi over 2 to leave us with, yep, that's all, 1/2 times 22 pi over 2. Finally, that's just 11 pi over 2. So that is the area of that region, right? So the main takeaway from this is that you don't necessarily need to know how to solve this integral if you're allowed to use the integral capable calculator on the test, right? It'll just be useful to know how to solve the integral if you're not allowed to use the calculator, right? So that is how you would do the integral. Now let's look at another problem like this, finding the area of one petal of the rose curve r equals 3 cosine 3 theta. So the trick with this one is that if you were to draw the unit circle, right, and it looked like this, you can see that this one of these petals is bounded between the radial lines pi over 6 and negative pi over 6. So that's the only trick with this problem. So it's pretty straightforward. Area is just change integral. We're going from negative pi over 6, pi over 6. We're trying to encapsulate the area between those radial lines. We have the 1/2 out front and our radius function, 3 cosine 3 theta squared d theta. So at this point, plug into your calculator. But if you have to do it by hand, it's not too bad. We can actually use some symmetry and just find the area in the top half of this shape. Let's just find this area, right? So let's actually go from just 0 to pi over 6 and just double it. So double that area, and that would give you the area of the entire thing, right? But the area, there was already 1/2 out front, so now the 2 and the 1/2 cancel. So not only is it easier to plug in a 0 than a negative pi over 6, but we also get rid of that 1/2 out front using symmetry. That's why I outlined symmetry in the first circle problem. So let's see, when we square this, we're going to get a 9 cosine squared of 3 theta, d theta, right? So area is 9 times the integral of 0 to pi over 6. Remember, cosine squared, let's call it u. Say u is equal to 3 theta for a minute. Cosine squared u is 1/2 plus 1/2 cosine 2u. So we're using these power reduction techniques that we learned in that trigonometric integral video. So if you want, go back and see that video. Now we have, if we plug back in u, 1/2 plus 1/2 cosine of 6 theta is what this integral turns into. 1/2 plus 1/2 cosine 6 theta. Still have that d theta. So we have, let's see, 1/2 theta. When you integrate 6 theta, we're going to have a sine of 6 theta, definitely, but what's going to be out front? Well, we can expect there to be an extra 1/6 out front, so the 1/6 and the 1/2 make it 1/12. That's because when you take the derivative of sine of 6 theta, you're going to get cosine of 6 theta, but the chain rule is going to cause there to be an extra 6 out front. So you'd want there to be a 1/6 in front of that for the 6 to cancel the 12 and leave a 1/2. Remember, 1/2 6 theta is what we started with. So it's kind of like doing a U substitution in your head. We're going to be plugging in pi over 6 and 0. We're going to get 9 times, let's see, pi over 12. Right, 1/2 times pi over 6 is pi over 12. And then we have sine of 6 times pi over 6. Well, 6 times pi over 6 is just pi, and sine of pi is 0. Okay, now let's plug in 0 into theta. We're going to get 1/2 plus 1/12 sine of 6 times 0. Well, again, sine of 0, or 0 pi, or any n pi, is 0. So now we have that area equals 9 times just that pi over 12, right? Or 3 pi over 4. So this is how we do the polar area. The trick is to use your calculator to solve the integrals, right? So unfortunately in this video I can't outline maybe a test level question. For example, these might be test level questions. Finding the area of the inner loop of this function, this polar function, or finding the area of the interior of this polar function, or finding the area of 3 petals of the polar function. You will have to rely on your calculator. You can put your calculator in polar mode and then type in the function, like you go to the y equals that you used to do when you graph functions in college algebra or calculus 1, and it's gonna graph it for you, and then you can trace, like it'll give you a shape like this, and you can click the trace button on your calculator, and in there you're gonna have something called a theta step. So if you set this, for example, your theta step to pi over 12, for example, that means every time you click the next button on your calculator, you're going to move another pi over 12. So for example, negative pi over 6 is the same thing as negative 2 pi over 12, right? And pi over 6 is 2 pi over 12. So when you trace in your calculator, it's going to start at 0. So when you click trace, there's going to be a dot that appears right here at 0. Then because of that, you set your theta step to pi over 12. You're going to move another pi over 12, maybe to here, which is, for example, or pi over 12. And then when you click it again, you're going to move to here. So that tells you that the top of this curve, or where you want your beta to be, would be 2 steps of pi over 12, which is the same thing as pi over 6. There's another way to figure out what this upper bound is. And then you can use symmetry to figure out that this is 2 steps backwards of pi over 12. You could also move backwards with the trace. So then this would be like negative pi over 12, and then your negative 2 pi over 12 here. And you get the negative pi over 6. So what if you were to make your theta step pi over 24? That is a common one to use. Well, you'd still start here, and then when you click next in trace, you're going to end up here at pi over 24. Then you click trace again, and you'll end up here again. Then you'll end up in another intermediate position between when you finally get to 4 pi over 24, and that's when you know when to stop. So you use this theta step to determine your alpha and your beta. So for example, if you wanted to find the area of this one, we know that what typically ends up happening with this shape is that it's going to shoot down this way as you trace it. That's why we did a lot of the orientation work with parametric. So it follows that shape. So for example, right here, when you finally go through this petal and you get back to the origin right here and you want to stop, that might be something like 18 pi over 24, right? So that would be your new alpha. And then you're going to click the next button, and you're going to end up here, 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 here. And when you finally get to the place where you want to stop, you record that step value as well. That one's probably going to be like 24 pi over 24, just a complete guess. So then you know that you could do the same integral from, like, for example, 3 pi over 4 to pi. That's what 18 pi over 24 is, and 24 pi over 24. You could do the same integral with those bounds. It would give you the area of this pedal, which would be the same as the area of this pedal. So just, that's a little bit of a, but I can't really show too much without showing the calculator. So to recap, you would put this into your polar calculator and use your theta step to determine alpha and beta. You're just going to keep stepping until you get to, for example, the beginning of this inner loop, and then you're going to, so if the shape looks like this, maybe your trace will start here. Maybe this is theta equals 0, right? You're going to click trace, and then you're going to go 1, 2, 3. You're going to start, so you know that after 3 steps, that would be the bottom of your integral. And then you count 4, 5, 6, 7, 8, 9, 10. 10 steps. So depending on your step size, that would be your alpha and your beta. And because you stepped, 7 steps in between 3 and 10, that would give just the area between the curves. That is how you use your theta step. But yeah, that's how you do area and polar. It's not too bad.